Hi everyone, my name is Nathaniel Bouchard, and I'm co-president of the Concordia Nuclear Engineering Society, or CNES. This presentation shall serve as a short introduction to one of our main projects this semester, the Cloud Chamber. So, first off, what is CNES? CNES is the Concordia Nuclear Engineering Society. We are a new engineering club which builds small-scale, safe projects related to nuclear energy and nuclear science. The first of our projects was this reactor model, so it's a model of a CANDU-6 nuclear reactor that we built and 3D printed and built last semester. We also have run some workshops and we'll be doing more of that in the future. This semester, our projects will be the Cloud Chamber and a reactor simulator, and then in the future we hope to expand to a fuser and all sorts of other projects. So, what is a cloud chamber? Cloud chambers visualize radioactive particles by condensing a cold alcohol mist. So down here you have a radioactive sample on a cold plate with an alcohol mist that's suspended over that plate. Now this is probably a little chunk of uranium ore, and you can visually see the radioactive trails coming off of this ore. Yeah, so it's quite an interesting device that lets you visualize these sorts of things. Now, we won't have access to uranium ore, but the radiation is present a little bit everywhere. We have background radiation everywhere. And there are certain things like potassium diet salt, which are slightly radioactive, but not radioactive enough to be dangerous. So potassium diet salt, you eat. So yeah, this is a short video of the radioactive trails created by a cloud chamber, and this is what we'll be trying to achieve. So, how do cloud chambers work? In a cloud chamber, you have some alcohol that you vaporize, and then you have a very cold plate at the bottom. You can use different sorts of cooling, so you can use dry ice or a refrigeration system. We'll be using more of a refrigeration type approach, but we'll be using Peltier modules instead of traditional refrigeration. Anyway, so you have vapors which come down, and then they form as they cool and approach this cold plate at the bottom. They form a supersaturated layer. So for the alcohol to actually condense and go from a vapor to droplets, there needs to be two things. First, it needs to be below its condensation temperature, but it also needs something called the nucleation site. So the same sort of thing happens in real clouds. For rain to come out, to come from clouds, you need tiny particles of dust known as nucleation sites to start off the creation of droplets and have those then fall. The same thing is happening here, except instead of small dust particles, we'll be using the ions that are generated when a radioactive particle smashes into molecules in the air. These ions become the nucleation sites for small droplets to form. So it will essentially rain inside the chamber at very specific spots, and that's what causes us to see our trails. So how do we plan to build our cloud chamber? So we'll build our cloud chamber as a group effort, which will be open to everyone willing to contribute and learn about this project. So we really will be open to anyone. You could join at any given time and contribute a little bit or contribute a lot, or come in with a lot of experience in CAD and heat transfer and all these sorts of things, or come in just looking to learn and involve yourself in something. So cloud chambers are actually pretty easy to build. All you really need is dry ice, a baking sheet, and a fish tank, and some alcohol. But we're not going to be doing it that way. We're going to be building a sleek finished product that will be full of features, because at the end of the day, we are engineers, not physicists, so it's a lot about the design of the machine and the whole process to creating the machine rather than just the experiment itself. So we're going to go through a rigorous engineering design process to create our machine rather than just buy some dry ice. This will have the advantage of indefinite operation, so we won't need to keep going to the store to buy dry ice to run our experiments. The whole machine will be manufactured in the makerspace. If you don't know where that is, the makerspace is in the 10th floor of the hall building, and it gives us access to 3D printers, CNC machines, really anything we would need to create most normal parts. And we shouldn't need anything too weird on this machine, so everything we can create, everything we'll be able to create on the makerspace. So the core features of our cloud chamber. So this plate in the middle will want to keep cool, and we'll need to keep it below negative 26 degrees Celsius, which is the temperature we'll need to actually condense the alcohol. We will use Peltier modules to keep it cool, rather than dry ice or refrigerants. The plate will be pretty large. It'll be 20 by 20 centimeters or more, which will allow you to view the trails and will allow you to have a pretty sensitive detector for things like cosmic rays, because you have a large detection area. This will also be nice for showing off at Frosh and different events, because people could see the trails from a little further away. So we'll also integrate a camera to count the number of trails which form around our sample or over a set period of time. And we'll have a screen to output temperature and the number of trails that we counted, as well as a few other things, whatever is relevant or interesting, potentially the power draw of the system, all those sorts of things. Then we want to implement a system for recycling the alcohol. So we'll need to pump alcohol to the top where it vaporizes. It'll come down, it'll condense down here, and then it needs to be collected and then pumped back up. So this will be an interesting engineering challenge, because there's so many little systems inside it that need to work together and in conjunction, which means that we have a lot of work to do and gives everyone an interesting part of the project to build. So how do I get involved in this project? Well, first you'll want to join our Discord, and the link for our Discord is right here. Then you'll want to fill out the membership form, which is also accessible on Discord, so you don't have to type in this link or anything. So when you fill out the membership form, you're just telling us your student ID and a little bit about why you want to be a part of CNES. It's not a formal application or anything. Then once you're in on the Discord, you can tell us you're interested. All you need to say is, I'm interested in the cloud chamber. How can I help? Ideally do that in the cloud chamber channel, which is only visible to members, so you'll see it there. And then you can join a work session. So the dates and times and locations have not been explicitly decided for this yet, but we will likely be meeting in H1032 and once or twice a week to work on this system together. You could also choose to work on your parts online. In person allows for more collaboration, but it's really up to you. So how will we organize our work? We have these different sub-modules, which are partially independent from each other. So for example, we can start on the Peltier coolers, the user interface, high voltage clearing field, and alcohol dispenser system without doing anything else. But then for the heat dissipation system, which would be the heatsink on the hot side of the Peltier modules, you'd need to have this part at least finished or well defined. So we'll need to know how much power or how much heat we need to dissipate through this system and all those sorts of things. So we need to define this system before we can do this and this. So that's sort of how we're going to split it. We're going to have these independent chunks that we're going to work on. So these different chunks require a little bit of everything from our different engineering disciplines. So it'll require a little bit of chemical and material engineering knowledge to determine the compatibility with alcohol of all these substances. So that's the first thing that's all throughout of the materials involved. Then there's some heat transfer involved in this part, as well as a little bit of electronics. The uppercase and lowercase are really mechanical CAD projects. Our user interface will be really electrical and computer engineering, as well as software, because we want to build an image detection model of sorts to detect trails. Then we will have our high voltage clearing field, which is a high voltage grid that makes the trails clearer. That will be an electrical engineering part as well. Then the alcohol dispenser, storage, and recycling will be pretty much entirely mechanical. And then the power supply requirements, all that will be electrical. So there is a little bit of something for everyone. The project is most heavy in mechanical and electrical engineering, but of course we will have computer engineering, software, as well as a little bit of chemical engineering. And this is a sort of thing that prepares you pretty well for work in the nuclear industry, where things are very interdisciplinary. It's mechanical, it's electrical, it's chemical, all at the same time. So, this is a picture of me, and as the lead of this project, I'm the main point of contact. So, if you have more questions about the project or anything about this in general, you can contact me either via the CNES Discord server, so you can tag me or other executives on Discord. You can put it in one of the channels, for example, the Cloud Chamber channel, and just say at Nathaniel, and then your question. The advantage of that is that someone else might be able to see it before I get the chance to and answer your question faster. Otherwise, you can email me, and this is my email below. All right, well, thank you for listening to this presentation, and thank you for your interest in CNES and in the Cloud Chamber and project in general. I hope to work with you in the future, and thank you.